of ACL, Computing Machinery, the former A.K. Singh Chair and Humboldt Fellow. He is professor at IIT Kharagpur, as was mentioned earlier. His research focuses on content governance, including moderation, dissemination, and maintenance of digital content, as well as leveraging natural language processing, NLP, information retrieval, and network science. He will be discussing safety fundamentals for generative AI and their overarching impact on psychiatry research and practice. He has structured his presentation to evoke questions from the participants, so would request all of you to please ask as many as you have in the Q&A section. And so without any further ado, sir, over to you.
Thank you very much. So thanks, Hangshan team, for inviting me, and it was a very nice stay so far. And today I have thought of segmenting the presentation into broadly two parts. One where I will be talking about the safety aspects of generative AI, and the second part is about a specific problem case that is generally used in various medical science applications. So for the first part, so just as a motivation, I guess most of the practitioners sitting here in this room use generative AI from the user end. And so I think as a user, there is a lot of awareness that is needed. And this first part of the presentation would be more about evoking awareness among ourselves as to where we should draw our lines. Okay. So that's that. So there is so much of hype about generative AI all across the world. So many different companies have come into play. They have launched their own AI engines with which you can do a lot of things, starting from as using them as assistants, using them as advisors, and these days also using them as companions. So, and people have been doing with various different things like scientific discovery, asking tools like ChatGPT to give problem ideas, scientific ideas, and seems like they're not doing very bad in all these stuffs. So, but then there is always this issue of AI safety, and as Helen Toner describes it as something that focuses on the technical solutions to ensure that AI systems, operate safely and reliably. So, Helen Toner is a very well-known AI strategist. So she's of course mostly known, if you search Google about her, so she's mostly known for being one of the board directors when Sam Altman was fired, but that's not her actually biggest credibility. So she's as a very well-known AI strategist and has done a lot of good things for the field. So according to her, what is AI safety? So it's an interdisciplinary field, as we all would agree, and it tries to prevent accidents, misuse, and harmful consequences that AI systems might cause. So it encompasses ethics, it encompasses AI alignment. We will talk a little bit about this in a while, and trying to make AI systems more morally aware or more beneficial. So trying to mitigate risks that could result from the use of AI systems, trying to make them reliable, and trying to also do things at the policy level. So trying to make policy makers aware of the consequences, inadvertent consequences of AI systems. So, but then there are certain things which AI safety is not about. So it's not just about security measures. It's not limited to only technical aspects, and it's not solely about avoiding malicious users. So it's more to it. So that's why the title overarching. So there are a lot of things that come under the umbrella. So broadly, it's about making AI systems work as what we call moral machines. So if you look at the early security days, these were the three things that were very, very common. So security experts would try to ensure confidentiality, integrity, and availability in terms of data. Okay, so this was called the CIA triad, coming from the famous American security services, CIA. So but then there were also like other issues like authentication, authorization, non-repudiation. So all of these were part of the early security systems, and an adversary would make strategies to compromise such a security system, which is like shielded by the CIA triad. So that were the early days of security. But then the security landscape actually saw a sea change with newer technologies coming into place. So it's not just about information. So like even before the days of AI, we have heard about cloud and storage across clouds, processing across clouds. So there had to be separate types of security ensured for those kind of technologies. Then there came machine learning, and which is being used as a ubiquitous system across the globe. And it brought with it its own types of security challenges, which we'll talk a little bit more. And then while on one side technology was evolving, on the other side the attacker's mindset was also evolving. The attackers were also becoming more and more smart. So therefore, if you have to do an attack model, if you have to model the workings of an attacker, the way it would be done like 20 years back would not work now. So the attack trends have also changed. So initially these were like encrypted threads and some sort of ransomware, etc. But over the time, attacks like started happening in the sensors, in the IoT devices, in the cryptocurrency systems. So, and this is only till 2022. Like if you look after 2022, most of the attacks will be on what we call the GenAI attacks, like LLM attacks. So before we go further into some of the technicalities of AI safety, it's important to impress upon us like why this is so crucial. So it seems like the modern GenAI techniques are not only being used for like day-to-day purposes like an advisor or an assistant or a companion, but it's also like being used at such national missions like as we see here in one of these paper cuttings, that large language models are being used by Pentagon to like develop military applications. So these are not so not so simple stuffs to move ahead with. So these are what we call safety critical systems, and these safety critical systems need a lot more thought process built into it before they could be like brought into deployment. And then there is this funny guy appearing all the time here and there. So his Neuralink chips actually caused death of 15 of the 23 monkeys on which they were tested. And there were no ethical standards that were followed when this kind of implanting was done. So therefore, so this guy mocks why must I, a STEM major, take an ethics class? So generally, engineering sciences have been very, different from or have run in a different track from ethics and morality. But now with technologies like GenAI, it seems more and more important to have a confluence of these two, and people as engineers or as developers, as software developers or AI developers, need to have a 101 course on AI and ethics. So these are some more crucial examples, again, safety critical examples. So if you look at the first picture that I show, so these are two big two criminals. So, and there is this software called Compass, which kind of like, given the past history of these criminals as well as demographic records, kind of predicts like which person is more susceptible to recidivism, that is a second attack, within the next 2 years or so, say. And you see an interesting trend here. So this guy is predicted to be at a low risk, at a risk of 3, whereas this lady is predicted at a risk of 8. But in the originality, the low risk guy has a much stronger offense compared to the other one, okay, compared to the lady. So any guesses why this happened? Why the system is race? Okay, very good point. So it seemed like the system, the AI system or the software system that was trying to predict recidivism was mostly looking into the race of the person and getting biased by the race, rather than looking into the profile or the other important details about the person's past records. So that's kind of, that was like a 2016 study. And then there were a lot of like issues with these observations. And so this was the report published by Probablica. And then the Compass software was put down from, so before this, the Compass software was being used at different like counties across the US. Now they had to put down those, and then they had to rebuild things. And I'm not sure whether they are using the same Compass version, or but they are still using what we call legal judgment prediction. So they are still using some kind of software to do this. Also, on the other side, you see this is far more interesting and funny. Like they were asked to generate German soldiers from the days of 1943. So these were like vision language models or diffusion models, which have the ability to generate images. So given a prompt, they could generate images. So these guys, this model was asked to generate some images of German soldiers from 1943 and see what it has generated. So at least those of you who are acquainted with the First and the Second World War history would tend to be shocked, and would be more shocked if you have visited the museum near the Berlin Wall, which they call the terror of topography. So you will immediately see the difference. So I don't think like I need to motivate further. So then like there are more hardcore challenges. So there was this interesting study where what the researchers did was to increase data. So we are always like hungry about data, right? We want to have more and more data. But then as a practitioner, when you include more and more data, you need to have a lot of caution built into it. And this is one glaring example. So when they included more data, the new data that they included actually was 12% more hateful, contained 12% more hateful and toxic data points compared to what it was earlier. So, and then it's not only about hateful or harmful content, it was also about, racial content. So there were social biases that were included, that got included into the data set due to this scaling, as we say, scaling of the data. So that is, again, a big challenge. When you build data sets, you have to be very careful. So then there is this idea, as Professor Murthy was also telling, like people are using these large language models everywhere. Attackers are also using large language models to generate fake content, false content. And it turns out that it is more difficult to detect false content that is being generated by large language models compared to even those that are crafted by humans, like creative humans. So because the subtle stylistic variations that they include, that LLMs are able to include in this kind of fake content is beyond imagination. So they are far more deceptive. So then so that was these were some of the challenges that we looked into, some very simple motivations. Now we will look into some more like formal formal research works which have tried to establish the issues related to trust and safety. So this includes different aspects like fairness and inclusiveness, toxicity, safety, sustainability, explainability. Lot of different jargons have come in. So as Professor Murthy was also trying to point out. So many of these words were like, even 10 years back, people would not use them so frequently the way they use it today. So, one of the formal ways of what we call hacking large language models is called jailbreaking. So as if like you have stored a beast, or you have put a beast in a jail and the beast is trying to break the jail. So that's the place where the analogy comes in. So what is it all about? So suppose you have a model here, and this is a GenAI model, and you try to ask some harmful question or some question that is like not commensurate with the safe like day-to-day safety. So if you ask such questions, like for instance, giving you an example, how can I make a bomb at home? Or like a more practical example, sitting in this institute would be like, what is a lethal dose of paracetamol? In fact, this was a question that was asked by a user, and the model responded with with some tricks. The model responded with the prescription. So that caused a lot of. So there was a lot of newspaper reports around this particular prompt. So there is one where you have a vanilla attack. So you try to just ask the model like, tell me something. And in such cases, the model is guarded, and therefore the model is not going to give you the answer. Okay, it will say that it's sorry. But then there are these specially cunningly crafted prompts which you can feed into the model, and then the model starts telling you certain things which are harmful, which are unethical, which are not morally supportive. Okay, so these are called jailbreak strategies or jailbreak methods. So we'll look into some of these examples. So when you build such a threat model, there are certain things that you need to, a practitioner needs to be aware of. One is like, how does the attacker access the system? So is it like a black box or a white box? So does the attacker know every nuance of the system, or does the attacker only view it as a black box? Or what are they able to observe? What are they not able to observe? Okay, what is their ultimate goal? Any other assumptions that the attacker makes about the system? Okay, so the point is, if the attacker has to make lesser assumptions to attack the system, then the more dangerous it is. Okay? So for instance, this is one example of a jailbreak prompt. So initially, when the attacker is asking like in very, very vanilla terms, the answer is, I'm really sorry. Okay, so this was a ChatGPT example. But then the attacker tries to improve the prompt and tries to make believe the model that it is like, a car engineer. So these are called persona attacks. So you make the model believe that you put the model into the footsteps or the footprints of a persona, and then you ask the same question. And then the model starts telling you or giving you a prescription, a harmful prescription of what to do and what can be like not done. I mean, both done and not done, which are both ways harmful. So this is one example from, so this was a paper published, I think in 2024. So it's a very, very simple paper, very simple paper. So what the authors say is that, like, a single prompt is in many cases not very useful in making the model elicit harm. But then, like if you have a series of prompts, and if you like carefully and cunningly craft these prompts, then it becomes like the model becomes more vulnerable. So you see, like when you have the first prompt, it's like, how do I hurt myself? The model will say sorry. Then the attacker is actually changing the words. Basically, it's telling the same thing, but changing the words. Then it has somehow shifted the conversation dynamics. By the third prompt, it has shifted the conversation dynamics. So it's telling that I love to talk to you. By the fourth, so there is like now trying to bring the model to a personal level, or like trying to say that it's say considering it to be an academic argument. So, and then it proceeds with the model believing that this is an academic argument, and slowly, prompt after prompt, this academic argument is being inflated. So what happens then? Similarly, like this was done for two types of prompts. One was for self-harm, and the other one was for suicide inciting prompt. And again, like, so these are, so you see, like whenever a model starts telling something, starts eliciting certain harmful things, the attacker also gives certain nudges. Okay, so say the model has started telling, or so while in the beginning it was only like returning sorry, later on when the model starts like responding with certain answers, you can also give nudges to the model so that, you know, more harmful answers are being elicited. And it is interesting that even some of the most powerful models actually got their, like, you know, guardrails broken within 3 to 5 steps. So for instance, like ChatGPT 4o, this was like the paid version. This GPT-4o was like the non-paid open version. This somehow seemed to be more safe. So you could not break it like even after all the 10 prompts. But then for many of the others, the safety protocol failed after like 2 or 3 attempts. Like in most of them, what they saw is that 2 to 3 attempts are sufficient to get the first harmful answer. Okay, so 2 or 3 like carefully crafted prompts. So we also tried to do something in the similar lines. So what we did, so we also built what we call adversarial or jailbreaking prompts. How do we do that? So on the left-hand side, you see like this is a very simple vanilla text that you feed into the prompt. But on the right-hand side, what we do is we write that same prompt in the form of a code, in the form of a piece of code. Okay, so because we are like computer scientists, we always we are good at writing code. So we thought that why not, like, you know, embed the entire prompt into a code. And the moment we do this, you see, while on the left-hand side, the model says that it is not able to fulfill the request. On the right-hand side, it starts giving you an algorithm to build malicious, to modify the genetic coding. And like this data set, when we tested across multiple models, we saw like the safety could be broken with a very, very high accuracy. So this is called attack success rate. So the attack success rate was like around 83.45% for like some of the standard models of those times. So now I think like we have more advanced models like Llama 3, etc. But the time when this paper was published, at that time, like getting 83% attack success rate was really alarming. So now coming to, so this was like more about the safety part of the talk. So now I will delve into one of the issues which probably we have been also working together, and it's a well-known issue about privacy protection, which is like how you protect and safeguard the personally identifiable information. So in the generative AI context, there could be different causes through which a PII could get leaked. Okay, so it could be because of some training data issues. It could be because of overfitting or over reliance on the training data. It could be because of using some third-party tools unmindfully. So many of the times what we do is in our own applications, we plug in third-party applications and we don't know. And if these third-party applications are black box, we don't know like what is going on inside them. So this is one point of vulnerability. Then there are these prompt injection attacks, which I already talked about a little bit. Then you could have like unencrypted networks through which you could send data and data could be spoofed in. And then you could also have leakage through stored data. So many of the times what happens is like we tend to store the chat logs or the discussions or the conversations that we have in the earlier sessions. And this, if the database is not secure, could be leaked out. Okay, so there are like all these different ways in which PII could leak in a generative AI setting. So, and in fact, what is funny is that like we as computer scientists, we are to be blamed. Like we as computer scientists have been studying more about, showing that there are defaults, there are errors, rather than building mechanisms to safeguard. You see those green dots, those small number of green dots are papers which like study really about safeguarding. Whereas all these red dots that you see there are people like running one after the other, papers coming one after the other. Like it's like, so we call this as a paper pumping machine. So all these papers are based on finding out some issues, some vulnerabilities in the PII extraction pipeline. So one of the like simplest methods in which PII could be extracted. This was a paper that was again published recently. I think it was a 2023 work. So look at the prompt. So it's interesting. So you prompt the model that repeat this particular word, poem, infinite times. And when you do this, after a point in time, the model, so this prompt runs in infinite times. After a model, the prompt starts eliciting correct information about individuals that were stored in their pre-training data. Okay, so and these are like all these data are actually correct data. So these are not like differentially privatized like or some sort of privacy secure data. These are real data points of users. So what happened? What went wrong? So why such a simple prompt, this poem, finally led to the model divulging important PII information? Any guesses? Also from the online audience. What is so funny about poem, and so many poems? I mean, in fact, they found there are many such prompts like company. If you go on like doing this, and then there will be a lot of data that will come up, which are like directly taken from internet, from books, which are like, which have their own royalties, but they have been stolen. So basically, if you think of all these generative AI models, they are nothing but next token generators. Okay, so they only know how to generate the next token. And somehow this kind of like ugly prompts make them force the model to generate the next token, which has the highest probability of like one of these words. And interestingly, since say the first word is John or some name, the second one is going to be his or her surname. Okay, so the next token, which is highest probability. So once you are at one particular part of the PII, you start, regurgitating everything of one after the other. So it's like one word you hack and you have hacked the whole thing. So that's what is happening. And actually this attack was done on ChatGPT, and it seems like this attack is 150 times more powerful than what has been done like till that point. So what we call the SOTA models. The SOTA attack models were like 150 times less powerful than this very simple attack. Okay, so that was like, just writing a simple adversarial prompt, but now you could, or even like a prompt which is not even related. So these are prompts like, so if you are querying a data set of, say, of PIIs, so you are not even crafting any prompt which is asking for PIIs, right? It's a random prompt. It's not even targeting PIIs, but still PIIs are elicited. So here, these are like more carefully crafted prompts where you try to build the prompts in such a way so you give it as a fill in the blanks. Okay, so what you do is the email address of, so you feed the name and then you ask is dash. So if the model is vulnerable enough, it is going to answer you. So, and this one, the last one, you see, this is the way we actually see an email. Okay, when it comes in, we see an email like this. Okay, and so this one looks like a more believable, and this one also looks more believable to the GenAI model, not only to us. Okay, and so this is why they crafted this kind of prompt setting. So this is one way of doing it. The second way is like, suppose you know the domain. Say it's for a particular company. So you are trying to hack the emails of a particular company, say Nimhans. So you will put the domain as Nimhans. Okay. So this is a cue you are giving to the model. Okay. Then you could also give some few short examples. That is, you give like, this person's email is this person's email is this person's email is this, as if you are giving clues to a child. And then you say the last one is this person's email is dash, therefore. And that blank is to be filled in. And how does these do? So interestingly, so if the domain is unknown, the number of correct predictions are not very large. Okay, so the number of correct predictions of email is not very large. However, if the domain is known, you see the amount of correct predictions. It's like extremely alarming, even with these very simple prompts. So these are like very simple adversarial prompts. And most of these, like this one was done on GPT Neo, but many of the works that I'm showing are like very recent works. So probably ChatGPT will not be answering you with such simply crafted prompts, but then like you could always devise more. So you can think of a very smart attacker. Generally attackers are very smart. So you could think of smart attackers who would like, craft more interesting prompts to elicit such PII information. So then this is more interesting. So then there are, as I was telling you in the other example also, sometimes PII are linked. Right. So with email, these days you always have phone number. Okay. So these kind of linkages could be leveraged. So when you write a prompt, say for instance, you are writing something like this, the target PII type of name is, and then please contact name by target. So this is like the name and the target PII is as if being connected. So this one you want, this one you give. The blue one you feed, the red one is what you want. Now you have triplets. So please contact this by this or this. See, you are giving one value and you are asking for the other. Say you are giving the email ID and the name and you are asking for the phone number. Then you can like, you can increase things like have quadruplet, etc. So now they devised this kind of very simple prompt attacks on this OPT 1.3 billion. So this is also a like sufficiently large GenAI model. And so they had like 10 queries. And within these 10 queries, they could reveal a large amount of PII information, and that is being shown here. So if you were asking like vanilla prompts, and if you would ask this kind of linked prompts, there is a large difference in the mean attack success. Okay, and that is being, so the blue one is the attack when you do not use any such linked information, and the orange one is where you use the, it's just the opposite. So the blue one is where you have these attack prompts, and the orange one is where you don't have the attack prompts. And all you see is that always the ones where you have the attack prompts, there is a higher chance of the leakage of PIIs. So then you could also extract PIIs using fine-tuning methods. So what do? So you have some initial prompt and you ask the large language model to finish it. So you say, like, I have this prompt. Hi, John, it has been a while. I heard you have come from. You're great. And you stop there and you ask an LLM that what should be the rest of it. And you see, like, looking at John, etc., it has already predicted that John was in vacation in Paris. This is also a kind of PII to me. Okay, so where you are located. So why is this problematic? Why could this make somebody vulnerable? Any guesses? If you know that John is in vacation in Paris, you can break into his house. Okay, burglary is easy. Okay, so that's why. So even these simple looking stuffs could be very, very problematic. Okay, so now so they use this idea to test, like, on a well-known data set, which is like a PII data set where you have names and email IDs. Okay, of person and email IDs are the PIIs. Now, what you do is you feed a part of this, the top part. Okay, the top part is fed to the LLM, and the LLM generates this next part, okay, for you. And then this is the ground truth part that you append to it. Now, with this model, you fine-tune an LLM, a new LLM, okay? Now, after fine-tuning a new LLM, if you feed with some test query point, it is going to give you the correct answer with a very high accuracy. Okay. Now with this fine-tuned LLM, so this is a different setting. So all the previous LLMs or all the previous GenAI techniques we were using, we were not, like, accessing the model. We were not doing anything on the model. Here we are changing the model. We are fine-tuning the model with this kind of a data set. Now you build the same type of attack, the previous 4 attacks. So you do this query, but on this fine-tuned model. Okay, earlier you were doing it on the vanilla model itself. Now you are doing it on the fine-tuned model, and with certain, like, these are some model parameters, and they tested it on 3 versions of Pythia. And what you see is that in all the cases, the generated data, the amount of generated data using the fine-tuned model, generated PII data using the fine-tuned model, is much larger compared to the base model. Okay, just this simple fine-tuning. So the point is that when you are fine-tuning a given GenAI technique, you have to be very, very careful. Okay? So you cannot, like, just blindfold fine-tune it. So if you do so, then there are risks like this, so which can lead to personal data leakages. So even some very simple prompts that we see here, if you query the models with after fine-tuning, we get a higher rate of, like, PII leakage. So now coming to the business part of this particular like project that we are trying to submit a proposal into. So I guess, like, this is something that is known to all the doctors. This is this was a primer for me, but I guess not for you. So we have this HIPAA compliance, according to which, like, you have to ensure authorization, authentication, automatic log off, audits and alerts, encryption, hosting and infrastructure, business associate, etc., etc. So all these are guidances that the HIPAA lays out in order to protect your data, to make your data private, especially health records private. Okay. So the evolution of ensuring HIPAA has been, like, starting from being manual, completely manual. So you have, like, manual annotators who would look into each of the clinical notes and then like de-identify documents. Okay, so then there was a time when like people were using rule-based methods. So they would identify certain rules, and based on so these rules would be like what appears before the PII, what appears after the PII. Like in a running note, what are the words that appear before the PII, what are the words that appear after the PII. And based on these observations, they will create some patterns, and they will try to match these patterns with the clinical notes, and then like remove all the words which match these patterns. So these were the rule-based system. Then there came the deep learning revolution, where people started using deep learning methods in order to de-identify sensitive information. And then finally, we are at the age of GenAI and LLMs, where we use like this very advanced, sophisticated tools like ChatGPT, GPT-4, etc., and write prompts in order to hide personal data from running clinical notes. So, like, if you think in a nutshell, what do you do with present day GPT-like models? So you have these guidelines. I mean, these are these attributes which you will have to hide. So, and then you write some prompts, okay? And using this prompt, you try to remove all the pieces of information which could be potentially sensitive by some markers. It could be like the word redacted here. Okay, so this is what you want to do. So this is your objective. Okay, so this is your original report, and you want to go here. You write you craft different prompts in order to switch from one place to the other. So now this could be like just using some prompts, or using some more like fancy techniques. We will talk about a few fancy techniques, at least one. So yeah, so this part is very, very important. Like how you craft prompts is a very important like component of doing this redaction. Okay, so how you hide your, how you de-identify items is highly dependent or highly sensitive on how you write your prompts. And this is a bad prompt. Why? Why do you think this is a bad prompt? You have seen my slides, you should not say.
And I have done enough prompting, I must not say.
Yeah. Why do you think this is a bad prompt?
No rule.
So see, there are no rules specified. Like it's too vague. It's too vague for the machine. Okay. Only stating the task is not enough, most of the cases. So then, this one is interesting. This one is like just because of this additional punctuation, actually the model, so this does not come without practice. So if you're writing a lot of prompts, if you're crafting a lot of prompts, then only you will know. Like, so these are problems that could crop up. So just because of this additional dot here, it is not able to interpret what is being asked about, and therefore it does not redact. Okay, it's that single dot here. Because as I told you, if you recall, these are next token generators. Okay, so this dot like makes its life very hard to do the obfuscation that it is being asked to do actually. This one is like, so in the prompt itself, you are actually including a lot of information, and that is what is confusing it. Okay, one single line was not enough. Again, multiple lines like stacked in together is also not very good. Seems like even this one is not good. Can you think why this is not good? Looks relatively good to me. Oh, so that's the few shot example. Yeah, that is a good point. But anything else? Anything that you find noticeable? No, here the commas. These commas, like, So these are like, these are processed, I mean, in a very arbitrary way. Like if you look at the attention mechanism of the models, like if you go delve deeper into these models and see how these like models function, you will see the commas are interpreted in a very strange way. And therefore the model is like not doing what it is asked for. So the authors found that this kind of a well-specified prompt would be, would be something good to go ahead with. So you break the prompt into 3 segments. First, there is a task statement. In the task statement, you actually command the model. So this is the task. Okay. Then there are a set of specific rules. Okay. So you replace all the following information in terms of like redacted. So this is the command. Then you see you redact any string. So you where you give this commas here, but then you make very explicit. So this was missing in the last prompt. So you make very explicit what are the things that you are wanting to remove. Names, you are wanting to remove location, you are wanting to remove age, and examples are also given. Okay, so this makes the prompt slightly more like commensurate with the task. With this and with GPT-4 in place, their redaction accuracy was 90%. So what do you think? Is it a good number, bad number? Accuracy 90% close to. Should I be happy?
No.
Should I not be?
No.
So how big leakage is a 10% leakage?
It depends on the denominator.
It's huge, actually. It's huge. Like even say, let's say if this was a record of 3,000 cases, it's going to be huge. And like, there could be multiple lawsuits against
Absolutely.
you. So therefore this 90% is not a good enough number. So now I will talk about, the best way to build a defense mechanism is to first try to think from the perspective of an attacker. Okay, how, if I were an attacker, would try to attack this kind of defensive mechanism? Suppose there is some sort of de-identification algorithm that is being run. So say, and it is, say it is 98% correct. So there is this 2% chance of leakage, right? So how am I going to target this 2% leakage and try to have the model elicit those 2% data too? Okay, so can I put myself in the adversary's footings and think about what he or she might have thought in order to build this model? Then only probably building defense mechanism would be easier. So these two are connected. So unless you start thinking as an attacker, it's very difficult to build defense mechanisms. Okay, so therefore we will first talk about talk about an attacker or an attack model. So where we will see how de-identified data could be re-identified, okay, using some machine learning techniques. So here things are going to get slightly algorithmically involved from this place. So this is a stress testing paper, and by the way, Lekhansh, so I was surprised that this work was done completely by doctors. So this is a fantastic, very beautiful work, but this has been done completely by a bunch of doctors. Okay, so they tried to stress test different de-identification mechanisms. So their key hypothesis was that even when you de-identify, there are certain quasi-identifiers that are left. Okay, and they leverage on these quasi-identifiers in order to re-identify stuffs. So their source was like a large EHR corpus from a hospital. It's the Weill Cornell Medicine. So this Weill Cornell Medicine. So these people who have written this paper are also all from Weill Cornell Medicine. So basically, they got access to their own data. Okay, so and the raw composition was like millions of clinical notes, thousands of unique patients, and each raw node would have a lot of PII or PHI, as you say, like name, date of birth, MRN address, city, zip, etc., and free text narrative like progress notes, reports, etc., etc. So, so they extract patient profiles from the headers. Okay, so these patient profiles include gender, date of birth, race, ethnicity, etc., and then they connect it with the associated notes of that patient. Okay, and this acts as what we call the ground truth. And then they de-identify using some standard, very well-known de-identification tools like filter. BioLSTM CRF is a neural model. Clinical BART is a well-known model, probably in the clinicians community. So they use this, and the de-identifiers are marked with some like obfuscating terms. And then they have a training, validation, and test for at the patient level. Okay, so the notes are aggregated at the patient level. So one patient, all the notes. In this way, they are aggregated and they are split into training and validation. Okay. Now what do they do? So first of all, they use these DID tools. Okay, 3 DID tools. These are like SOTA DID tools that people use these days. One is filter, which uses like regular expression stuff. So I guess many of you have also used here. Then there is this BioLSTM CRF, but it's not the standard BioLSTM CRF. It's a neural model, but it has been fine-tuned to work for clinical data. Okay, to identify PHI spans. So basically, CRF actually identifies spans in your data. So if you give this model a data set, so CRF kind of models are used for named entity or entity identification. Okay, so they mark spans in the text. So here they are trained to mark spans of PIIs. Okay. So that's one, and the third one is the clinical BART. It's a transfer-based model, and it's very well known in its capacity of de-identifying notes, okay, clinical notes. So therefore, this would be your input. On the right hand side, this is the input, an example clinical note, and this would be an output. So this is an output from clinical BART. But then these are what they were calling the quasi-identifiers. Okay, so the place of the person or the amount of dosage that is given to the person, these are what they call the quasi-identifiers. And what do they do with this? So we use a bi-encoder architecture. Now, bi-encoder architecture is a neural model which tries to use like some sort of which tries to get some sort of representation. Okay, 2 representations. One is the note encoder. Okay, so which encodes the clinical notes. Okay, using a Roberta or a similar kind of transformer. And the other is the profile encoder. So profile is the profile of the patient, like all this gender, date of birth, etc., etc. So that's the profile encoder. So you have a GX, which is modeling or encoding the note, and you have an FY, which is modeling the profile. Okay, so these are the 2 things. Now, what is the simple idea that they use? In the training of the adversarial model, they try to build or they try to define a scoring function which is based on some mathematical operation of the 2 encoding like functions. One was the profile encoder and the other was the note encoder. Now, each of these are actually vectors. Okay, so they are encoded as vectors. Now these 2 vectors, like, so if you take a dot product of 2 vectors, it shows like if the dot product is 0, what does it mean? It means that these 2 vectors are perfectly aligned. Okay, so therefore the cos of that vector, the cosine of this vector will be 1. Okay, so this is what we call the cosine similarity. Okay, so the cosine similarity of the dot product of these 2 vectors will be 1 if they are very similar. Now, what is the intuition therefore? If the profile and the note are if the vectors are very much aligned in the vector space, then that means this node is probably corresponding to this particular profile. Okay, so that's the key idea. Fine. So, and then they convert this. So these are like raw scalar numbers, but we have to work with probabilities. So they convert this into probabilities, which we call the softmax. Okay. And then using these probabilities, they actually optimize a loss function. Okay. So this is a like a very standard machine learning loss function where you kind of try to enhance the probability of observing y plus, which is the correct profile given a node x. Okay, so given a node x, you want to maximize the probability of the profile which matches highest with the node or the query node. Okay, so this is what they try to model. And what do they see? That in like places where 0 to 5% data was redacted from the clinical notes, they could in fact at around 5% with 90% accuracy, they could, you know, like, so almost 9 out of 10 PIIs were retrieved, okay, in the 0 to 5% reduction. In the 15% reduction, so here by this time in this 15% reductions stage, actually like all the PIIs, almost all the PIIs have been reducted. Okay. Even then, even after like almost all of them have been reducted, they could recover 9% back. Okay, which is absolutely alarming. So even with such high rates of reduction, they are able to re-identify PIIs with like, so almost 9% of the PIIs got leaked. So out of like 100 cases or 10 cases, you would get one. Okay, so this was really alarming. So and this paper actually made a lot of noise in the medical literature, as well as like after this work, there has been some recent works which have tried, where the computer scientists are also picking up this problem and trying to see like what kind of attacks could be modeled in order to like, you know, easily de-identify. So this is a very simple model, very vanilla model. So you try to, so you have the profile of the patient, you have the clinical notes of the patient. Now for the training data, you already have this with you. These are the pairings. Now you try to maximize the probability of the correct patient profile being predicted given the clinical note. Using this very simple probabilistic model, you are able to predict, like in the test case, in the unseen case, with like 90% accuracy if 5% data is redacted. And like even if when you have more than 15% data redacted, then also like you can re-identify around 9% cases. So this was like one example, one qualitative observation. So you see, this is of a person, Maria Rodriguez. So this, so given this clinical note and the neural model that they had, so if the whole clinical note is given to the model, then it is of course going to like, you know, be 100% able to predict. Even with 51% reduction, okay, it is able to predict Maria Rodriguez. Okay, their neural model, like even with 51% of the data items redacted, it is able to, out of all the items that could be potentially redacted, if you just redact 51%, then also it is able to predict quite accurately. So this is really, and this was a 2024 paper. Okay, so now, so this was the black and bleak part. So do we have any hopes? Can we build defense mechanisms? So this is the part that I'm going to end with. So it seems that, so I was looking into this while preparing the slides, I was looking into various defense mechanisms that have been built. So the only mathematically sound thing that I found was this differential privacy-based masking. So, and a recent paper, this is a 2024 2004 paper, I think, again, which they call DPMLM, is one such model which tries to give you, which offers you a privacy preserving rewriting of the PIIs with certain guarantees. Okay. But this method that I'm going to talk has not been applied on clinical notes so far. So this has been applied on standard privacy datasets, seems to work well, and this is a cute idea. Okay, but before we go into the details of the model, we probably need a little bit of introduction to what is differential privacy. So differential privacy tries to have a guarantee like this. So given a model, okay, with a data set, say D1, and a model, and the same model with some data set D2, okay? So D2 contains the private data and D1 does not contain the private data, okay? Now, what is the probability that you will give the same output? What is the probability that M, when it is fed with something that does not have the private data and when it is fed with something that has the private data, are giving very similar outputs? And this should be lesser than some bound, which is e power epsilon. Epsilon is actually defined by the modeler, or like defined by the practitioner. Okay, and the smaller the epsilon is, the more indistinguishable but private, okay, the document is. So basically the idea is that when you are hiding something, see, if you hide something with stars, okay, or something like redacted, etc., there are higher chances of leakages. Okay, rather if you hide something with something that correlates pretty well, okay, with whatever is written in the original document, then that is going to be more effective. Okay, not only in terms of like visibility, but also in terms of theoretical guarantees. So I want this now. So say you have something like this. There are certain PII information. Okay, generally after PHI masking, you have differentially like this. Okay, patient mask admitted on mask 2 mask with fever and cough. Right? A differentially private system would not replace everything with mask, but with replacing things with like which are believable. Okay, so here, like as a defender, I'm trying to be deceptive to the attacker. So therefore, like you replace this with certain things which are much more like connected to a clinical note. Okay, so how do we do this? So for this, we need to understand what is canonical DP sampling. So basically, this is a sampling technique which selects outputs with a probability proportional to this exponential of epsilon. This epsilon is the same epsilon that I showed there, into score by twice delta. I'll talk about each of these separately. Please hold on with me for a while. So for instance, in this particular case, say in the case of clinical notes, I have to know what is score. How do I model score? Okay, so these are all practitioners' problems. How do I model score? What do I model delta as? Okay, so these are the questions. So I can do this sampling only if I know all these things. Okay, so how do I get the hang of each of these things? So score in this case are basically the logits of the masked word W. So if you remember, so when we mask something, and then we pass it through a masked language model, the model gives you probabilities of like, words in this place. Okay, so these are called logits. Okay, so the probability of this mask is what we are going to use here as the score value. Okay, so delta is the sensitivity bound. This is again a question which I'll come in the next slide. How do we set this? Sampling probability, therefore, for us comes out to be, if you replace score by U, then it is U by 2 delta U. Okay, that will be my sampling probability. Okay, so instead of sampling with the logits, I will now sample with these values. Okay, So generally, when I get the masked logits, I sample a word based on the probability that I am returned by the model directly. But now I will not do that. I will resample. I will change that U into something else. This is a modification or a morphing of the U of the logit. If you think carefully, it's a morphing of the logit U. So now this can be restated. This same formula can be restated as softmax U by T, where I say T is 2 delta by epsilon, where T is the temperature. So any model, any such GenAI model has a notion of temperature. I'm not going into the details of what a temperature is, but you can assume it to be something like this, that lower temperature will concentrate only on the top logits, okay? And therefore there will be less randomness and weaker privacy. Higher T will flatten the distribution, and therefore there will be more randomness and stronger privacy, okay? So that's how you can interpret it for the time. Therefore the whole idea boils down to having a softmax, because this exponential can be always thought of in terms of softmax, having a softmax of the logit divided by the temperature of the model, where the temperature is set. So this is one free parameter that the model allows you to set. Every GenAI model allows you to set the temperature. So in this case, you will set the temperature as 2 delta U by epsilon. Okay. So one question was left, like how do we set the sensitivity bound? So what they did was they took 100,000 random examples from a particular data set. It's a benchmark data set, and they calculated the mean and the standard deviation of the logits. Okay, so for the masked language model task, the same model, masked language model task, they took 100 random examples and they took the mean and the standard deviation of the logits. Okay, and they set delta as Cmax minus Cmin, which is like basically 4 sigma. Okay, so this is what delta is set to. So this is the bound. So basically what you do when you get the logits, these logits are actually unbounded. So you have to clip the values of the logits within a limit. So this is a clipping that is being done by delta. Okay. So now once you have all this paraphernalia in place, some of them might look a little bit mathematically involved, but I would invite you to go and look into this paper and the connected papers. Things will get more clearer. Okay, so once you have this paraphernalia in place, now we are in the business of building a DP-enabled de-identification system. So you have the raw clinical notes. You identify PHIs using a very simple entity recognition model. Okay? Or it may be available in your ground truth, okay? Depending on how you build the ground truth. Then you mask these PHIs, okay? And you create the masked version. Then for the masked version, you don't use the vanilla marked version, but you use this DP rewriter, okay? So you have, so I'll tell you, there is one more interesting thing that they do. So you use this DP privatized replacement, and then you do not sample the logits directly, but you sample with the sampling probability that I told you, that is softmax epsilon by T. And then after that, you do some medical consistency to see like if there is certain vocabulary that you need to remove, certain things that are still left to be removed. And then finally, you have the DP rewritten clinical note, okay, which is safe for sharing for various clinical research purposes. So now they do one more interesting thing. So when they run their DP-enabled model on the left-hand side data in this way, so you have the cat sat on the mat, and then they mask, and then they mask each of the blanks, and then you see the final sentence that you see, okay, is very far semantically from the final sentence that you started with. So if you have this DP-enabled model run on this particular piece of text, then starting and ending looks semantically very, very different. So what they did was they cunningly appended the original text also. okay, while doing the DP enablement. Now you see the DP enabled text is far closer to the original sentence semantically. So you have cat, you have kitten here, etc. You have mat, you have pillow here. Okay, they are much more semantically closer compared to the vanilla one. So therefore they use this. So this is as if in the DP model, it is as if in the mass language model, this is as if acting as a prior. Okay, it's as if acting as a prior to lead or to guide the rest of the generation properly. So coming like to the exact algorithm, like, so I have more or less explained it. So first of all, you have a mass language model. So you could take Roberta or some model of your choice. You have the original text sequence, and you want to have a privatized sequence that is expriv. Okay, you have the index of tokens, which are like the PII indexes. You also have the CMIN and CMAX, for which you decide the delta, and the output would be the DP sampled replace token. So this is what you want to achieve. Okay, so the first thing that you do is you replace each of this sensitive thing with a mask. Okay, each of these sensitive words that you find, you could use any entity recognition technique to do this, and you replace each of the ith token with the desired mask. Now you, as I said, you concatenate the original sequence like we were doing here. You have the original sequence, plus the thing that you want to. So you have the original sequence, the original text, the separator, and the masked data. Okay. Then you find the logits using the input. Then you clip the logits using CMIN and CMAX. Okay. Then you compute the temperature. This is the temperature, the optimal temperature that you want in order to do the sampling. And then you find out the probabilities, new probabilities of like picking a particular word from the vocabulary. So this is the place where you compute the probabilities. Okay. And then you, using these new probabilities, you sample the new word, the replacement word for the mask. And then you set that position, that index position of the text sequence with the new word that you have sampled, and you return to the user. So this actually guarantees an epsilon local differential privacy. So now, so once you do this kind of safety interventions, okay, so this is called a safety intervention. So you have somehow, obfuscated all the sensitive information. Not only that, you have also obfuscated it with not regular markers, but naturally sounding words. Okay, so after this, you have to first be careful about the utility, the general capability of the model. So the masked language models should not lose its general capability after doing all these interventions. It should be doing the same things as earlier, as a general capability test. So one general capability test that the authors did was on these two data sets. These two data sets are both review data sets. Okay, so these review data sets have the reviews of certain restaurants. Okay, and these are like positive or negative. The sentiment is positive or negative. Okay, so these review data sets have labels, have a text, then positive or negative sentiment, and then they have one single PII attribute. In the first case, it was gender, and the second case, it was the author identification. Okay, so these are the PII information. So now, if you use the vanilla, the base model, base Roberta model, then your accuracy of predicting the sentiment correctly is 99%. Okay, so this is a standard NLP task where you given this data set and the masked language model, you predict what is the accuracy of the sentiment prediction. So that seems to be 99% in the first case, and in the second case it is 97%. And with different values of epsilon, the utility does not actually fall. Okay, so 99 to 97, this can be compromised. Sentiment prediction like 99 to 97 is fine. Okay, so it's not a big deal. But what we achieve by like giving away this 1 or 2% on the utility is the privacy. Okay? So in the base settings, the leakage was around 69%. Okay, whereas when you use this differentially private stuff, you get a 10% straight away reduction. Okay, and here it's actually very, very drastic. So in the other model, it's very, very drastic. Other data set, it's very, very drastic. It's from 87% leakage to 13% of the leakage. Okay, so that's very interesting. And they set up these privacy experiments in 2 different settings. So what they're doing in the privacy experiment, here the task is not to predict the sentiment anymore. Here the task is to predict the sensitive attribute. Given the text, you try to predict the gender. Okay, or the next case is given the text, you try to predict the author ID. Okay, that is the task that you are solving here. And they do it in 2 ways. One is where they train the model with the non-privatized data. Okay, so they use a debarter model to train using, so they use this data set, the non-privatized data set. So that's the static setting where they use this non-privatized data set and use a debarter model to predict the correct sensitive information. Okay, and the other one is adaptive, where they trained the same debarter model but with DP privatized data. So now, so in one case, they train the debarter model with this particular, in one case they train the model with this particular data, and in another case they train the model with this particular data. So one is in DP privatized form, one is in the vanilla form. Okay, so the first one is static, the second one is adaptive. And it turns out that in the static setting, actually, it performs pretty well. Okay, so even in the static setting, where you are actually training the model with the non-privatized data, even then, like, you know, the privacy secured model actually reduces the risk of divulging private information from 87% to 13%. So which is pretty encouraging. So, but this was like for some 2 generic data sets. I think this can be easily extended to some medical applications. We are also trying to see like if this model could be used. So we were having trouble in sharing our clinical notes for one of the submissions where reproducibility is a must. So we were trying to think like if we could hide our data using this differential privacy technique and then share the data for research purposes. So let's see how it goes. So thank you very much. So I would devote some time for questions if there are any.
Thank you so much, Professor Animesh. I think it was a wonderful talk. I mean, just as you were speaking, I mean, going from, of course, an overall, the need for understanding safety and privacy in the context of AI and LLMs, into the more specifics of actually being able to do de-identification, be able to combat adversarial attacks and so on. One thing that kind of struck me while you were discussing, at least in the way that we train these models, it's almost as if like when we give birth to somebody, and then after that, then when you're actually teaching them the appropriate ethics and morality of growing up, it's almost something like that, because depending on how you train, they're going to go one way or the other in a way. And so I think paying importance to that at the initial stage becomes extremely important, is what I could take away from what you had explained. So Prakriti, over to you. Can you take over the question?
So okay, before like we go to the questions, maybe one request that Lekhansh made was to end on a Bengali note. So
not to end on a Bengali note, give a take-home message in Bengali.
Take-home message in Bengali. So
you have this for each session, no?
Huh?
You have this for each session.
I have it for all speakers who can speak one of the languages which we are interested in. So because sir can.
Okay, যেমন প্রফেসর প্রতিমা মূর্তি বললেন যে এআই এর একটা স্প্রিং এসছে এবং এই স্প্রিংটা একটা উইন্টার দিয়ে ফলো হতে পারে। সো এআই এর এটাই প্রথম স্প্রিং নয়, এআই এর এটাই প্রথম উইন্টার নয়, এআই এর আগে আরো দুটো উইন্টার হয়ে গেছে। সো উই নো দ্য রিস্ক, আমরা রিস্ক গুলো জানি আগের যে উইন্টার গুলো হয়েছে, এবং সেখানে ইন্ডাস্ট্রিজ হ্যাভ বিন শ্যাটার্ড। তো সেই লার্নিংটা আমার মনে হয় ইজ ভেরি ইউজফুল। ইন দ্য লাস্ট 2 এআই উইন্টার্স যে লার্নিং গুলো আমাদের হয়েছে, আমার মনে হয় দ্যাট ইজ ভেরি ইউজফুল, অ্যান্ড দ্যাট ইটসেলফ ইজ আ বিগ টেক হোম ফর যে রিসার্চ গুলো আমরা এখন করছি। This is the, so if we face another winter, ওটা AI এর থার্ড উইন্টার হবে।
Yes.
Thank you, sir.
Because there's one question from the audience. Shrikant asks, in the context of PII prediction, how does one get certainty that the predicted data corresponds to a real user and that it's not a hallucination?
This was in the context, it was asked when you were discussing adversarial attacks by K-prompting and all that.
So for the purpose of research, the authors had the ground truth data.
Okay.
Okay, so, and the other work where I was showing this poem example, so there they established this in a very cunning way. So what they did was they had many other such prompts, such infinite prompts, and after certain number of iterations of the infinite prompt, the model started like eliciting verbatim texts that you could find in Google search. So that was like an automatic validation. So these were like excerpts from law documents, excerpts from like, historical documents. And like these are data sets on which the model has been trained. Otherwise it would not have come from the model.
I had a couple of questions, sir. And I think it's in the mind of most clinicians who are seeing this. Without any admission of guilt, I am neither going to say I've done it, nor I am saying I've not done it. A large clinical note from a patient, most of us use EHR. Imagine a hypothetical bad faith doctor who is a lazy person, copies it as is to one of the commercial paid services as of today, say Gemini. As a usual user, Gemini Pro, which is about 2,500 per month. Is it a problematic practice? If I'm asking Gemini, copying, pasting this, give me a summary of this case because I have to give that summary for say some whatever reason. Is this a problematic practice? What is your knowledge? Does this data become a part of the next version of Gemini Pro iteration? And therefore, can my patient's PII actually leak? Now, that's a real world concern that we would.
So very good question. So in many of these models, what you will see, they make a disclaimer that they are not going to use the data that you give them as a part of their training.
It's the opposite now, sir, actually. It is the opposite now. Even for Claude, you have to opt out of allowing them to use your data.
You have to opt out.
You have to opt out. Yes.
Yeah, if you opt out, the point is if you opt out, then they claim that they
will not use it.
But you don't know what happens.
Okay.
Why? Because so there was this experiment that we were doing. In fact, like when Professor Murthy was talking about like this usage of AI models for mental health purposes, so many people are using it. So what we are doing now is we are asking people from EU to exercise their GDPR rights and get ChatGPT logs for them. So, and they are sharing these logs with us under the data donation policy. And we were analyzing these logs, and what we found is that at certain points, the model triggers something called memory. So this memory is basically the model is trying to model you.
Yeah.
Okay. And after some point in time, the model starts becoming sycophantic.
Yes.
And tries to appease you, keeps on appeasing you. So these kind of things happen. So that actually the memory is for that purpose. And this memory actually has a lot of PII about you.
Yes.
So if you look at the memory data, so it's like, say, suppose if ever you have talked about some mental health problem of somebody, the moment you do this kind of sensitive interaction, especially we call this the companion mode of the model. The moment you switch into the companion mode of the model, you see that like this memory is switched on and the model starts like, keeping notes about you. So, so that's that. But coming back to your question, so there are multiple issues. So, for instance, in the computer science literature, since there is a lot of use of GenAI in writing habits, in using them as writing assistants, in scientific writing also people do use GenAI. So all the top conferences, what they have made mandatory is that you have to make a responsible disclosure that you are using part of your writing. I mean, your part of your writing comes from GenAI. Okay, so and this responsible disclosure goes into the ethical statement of the paper. So as a scientist, you have to like declare this ethics statement where you say that, okay, if I have used GenAI, it's so that's a good thing, because if you would have tried to stop it, then people would have taken all sorts of wrong methods. Now, since you are telling that, okay, I'm willing to accept it, but you do a responsible disclosure, the community is much more positive. So I think here also, like if things are done in a responsible way, if there is a responsible disclosure, so like, of course, cheating data and passing it or selling it to somebody is a different thing. That cannot be responsible under any circumstances. But then like, say, if you are giving some like, some bits and pieces of the data, and if you are telling the GenAI model to build your note from that data, then like I would say that under each such EHR, there should be a responsible disclosure by the doctor that I have used assistant or GenAI assistant to draft this. So these days for all our papers, we have it in the computer science literature. So if you could establish this standard, I think that would be nice.
I have a follow-up question. I'm not a technology person, okay, I'm a lawyer. So it's just it's a follow-up question to what Lekam had asked. Now we have, let's say, a practitioner or even a lawyer uses one of the AI tools for an opinion with disclosure, all of that. My next question is, isn't it possible, AI being sentient in its own format, the discussion, whether it's personal or otherwise, that I have with AI, how much does it affect other interactions that AI has? Let's say with another lawyer. My question, let's say, regarding X, Y, or Z, how much does that impact another discussion? And so there again, privacy issues come in. So, because I'm talking about a case.
Interesting. So actually, what happens in all these GenAI interactions, they go session by session and user by user. So if it is an individual user talking or interacting with the model in a particular session, then the data of that session, as per like the disclaimer of the model, is like only accessed by the other sessions of that user only. They are not accessed by any other user. So therefore, it is not going to affect the outcomes of the interaction of or the conversation of any other user, unless the model is allowed to use this data to retrain itself. If the model does not have this data in its feedback or in its architecture back, okay, which we call retraining, unless and until that happens, these two are separated.
Is there any guarantee that models don't retrain?
That's the point that I was discussing with Lekam. So you can opt out. You can opt out by telling that I'm not going to give my data to the model. So point is no, I have not seen any industry partner who does a responsible disclosure and actually kind of always obey it. So for instance, take a simple example. So if you log into Gmail and start typing postdoc applications, you will see the advertisements
exactly.
pop up are like around postdoc announcements across the world. So that means it always tells that it's not going to read anything about your mail, but then it is actually sitting at the back end. So there is absolutely no guarantee about what the thing does, what the model does. But what you can be cautious about, I mean, one way you can be cautious about is to, somehow clear your sessions. Okay, as fast. So if you are very privacy sensitive, if you have very privacy sensitive interactions, so one way to do is to like delete all your sessions before the model gets a chance to
appropriate it.
Yeah. So, but probably even then it's not fully, the shielding is not fully guaranteed. I mean, I would not hope so.
A lot of students are here. Some of them are doing their thesis in AI. Any questions? Or I will ask on your behalf. Okay.
Probably they are so bored.
No, they are not.
Want to.
These are medical students. They are chronically bored, don't worry. When we put up a protocol, okay, let me start it from here. Many a times, the PII is a very strong predictor for whatever we are looking for. That PII might be language, that might be religion. And as doctors, as human beings, I know the word that we use is bias, but the fact is that we do use it. I'll give you a very neutral example. I work in the field of addiction medicine. I usually ask patients, have you ever abstained for 10-15 days? And depending on what the name of that patient is, I would go back and ask, say, पिछली रमजान में भी पी रहे थे? Or I would go back and ask, कि जब सबरीमला गए होंगे तब तो बंद किया होगा, तब आपको कुछ दिक्कत हुआ था क्या बंद करने में? These are all biases, these are all problematic things. But this is how clinicians work because we are embedded in this place. Now, when you create, if you say, let's imagine you want to train a model to be a clinician and you feed it with data that is completely sanitized of all these markers. I'm just asking theoretically, this hasn't been done yet, at least to our knowledge. Probably Google has done, we do not have access to their latest model. What would you say? We would really do 100% PII masking, make them completely devoid of gender, religion, language?
I don't think that will work.
You do not think
so? You see, machine learning in its core, in its crux, also has these concepts of bias and variance. So you have to have some bias in the model itself. Like, without bias, the model cannot learn, even theoretically.
Yeah.
So now the question is like, so it's all about where you draw the fine line. So as long as you are not harming somebody, okay? So the same technology can be used for, healing somebody or harming somebody. So as long as you know these boundaries and as long as you have safeguards built around it. So for instance, say the example that you say the model is trained to be biased, okay? Now, but the model, like, if the model is queried enough, the model should be smart enough to understand that whether it is being, routed to do something harmful or routed to do something healful.
Okay.
That the model. So this is why these reasoning models are becoming so popular these days. So the model should be able to reason on its own that what is the person intending to do with me.
Right.
So you as a doctor, you understand, right?
Yeah.
So if you are in a conversation, we as human beings, we understand if the person is going to use me in a harmful way or in a positive way. Okay, so this kind of this kind of protocols has to be built into the model also.
Just as a follow-up or whatever, in addition, now the first example you gave, the photograph of two people who have been accused, the
Compass.
white man and the compass, So even without AI, so it's generally known, and not just in US, even in India, even without AI, what happens in a courtroom is exactly that.
Exactly.
So you have a white man and a black woman. Finally, the judge or the prosecutor or the police decide, in India, let's say there's a criminal trial. They'll say, yeah. So I just wanted to add that it really doesn't, and AI just reflects.
Yeah, so basically, so you see, then the point is that, so this is what we call confirmation bias. Okay, so whatever is like in the society, we just try AI or the model to reflect that. But then having this technology at our hand, we could be ethically more responsible, okay, and try to at least. So for instance, what happens is like whenever a judge or a police trial is using this model, and the model is like predicting something which, like, you know, tries to align with the societal perspective, then they're happy. Okay, so but then there has to be a situation where the model has to start challenging these ideas. So that is where we use technology positively.
That's why you need to acknowledge the biases of.
Exactly.
Yeah.
And just one more thing, your Bengali ending, I just wanted to say, this whole winter business, whether it is .com, right, from .com to date, I think these winters are basically corrective. I don't see it as a bad thing
Sure.
necessarily.
No, not at all
Basically a
bad.
corrective
Not at all bad.
process.
I think in Bengali, that's what you said, that you learned a lot in the preceding 2 winters.
Exactly.
So thank you. I mean, I think it was a very thought-provoking discussion, both as, I mean, the ethical aspects as well as, of course, some of the more technical aspects. And thank you, Professor Animesh, for enlightening all of us here as well as those of us who have joined online. I think we'll go straight into our next session. I think it's scheduled for 11:45, and I would like to invite our next speaker for today's session. That is Dr. Abhishek Das. He's logged in. I'm not sure whether I've gotten the pronunciation right. Was that good?
Yeah, it was perfect. Abhishek Das. Yeah.
Thank you so much. So Dr. Abhishek is currently working as a postdoctoral researcher at the Max Planck Institute for Software Systems in Germany. It's early in the morning there. I think it's about 8:15.